happy to turn it over to Dr. Harmon.
Alrighty, so when I was preparing my IQ talk, I very much discovered that, wow, it sure is harder to prepare a 3-minute talk than it is to prepare a longer talk, because there were so many things where I'm like, I can't possibly not say this. This is so important. I have to throw it out. And so I thought, okay, maybe when I talk to the women in science folks, I can say the things that I really wanted to say for the IQ lecture but didn't have time to say. Plus, you guys are science majors, so that means that, you know, I can feel like I don't have to, you know, with the other talk, I'm like, well, if they don't know what protons and neutrons are, I can't help them, you know. Whereas I don't have to worry about that with you folks. So, the long version. Has anyone ever told you that you are star material? Is my title here, and as we'll see, that's because you are literally star material. So, what's this? Crickets. Right. It's a bunch of crickets. No, of course, that is the periodic table of the elements. Very often, I've had like a chemistry class come in after I'm done teaching a class in here, and so I'll throw it out to them. It's like, so you guys know where the chemical elements came from? And the answer is often no. And so I don't know if you guys know where they came from or not. Maybe you just kind of accepted them as they're just there, right? So maybe it's never even occurred to you to wonder where they came from. They had to come from somewhere. Maybe you've assumed they just all came out of the Big Bang. That turns out not to be right. So the point of my talk here is to let you know about that. So in fact, if your atoms could talk, then there's 2 things that would be true. One is you should probably be laying off of those mushrooms. The second is that they would have very amazing stories that they could tell you. But it turns out they can't talk, so I'm going to talk for them here. So if we're going to explain where the elements came from, then we're going to have to explain why some elements are very common and other elements are very rare. That must mean that whatever is making those elements is good at making some elements, not so good at making other elements. And you might first think that maybe what we should do to get some sense of abundances of elements is just study how common they are on Earth. But Earth is weird, cosmically speaking. Terrestrial planets like Earth in general are weird in that they have very atypical compositions compared to the rest of the cosmos. Our sun has about 1,000 times the mass of Jupiter, and Jupiter has about 2.5 times the mass of all the other planets put together. So that means that if you want to know what is the chemical composition of the solar system, you need to study the sun. And that's true for the other solar systems that we're now discovering in abundance. It's always true that stars are much more massive than the planets that are orbiting them. So if you want to know what's the chemical composition of the universe, stars are what you want to study in order to determine that. So here's a figure from Wikipedia that has solar elemental abundances. This is by number, and it's based on the strengths of absorption lines in the sun's spectrum. Now you should note that it is a log plot. This is the log base 10 of the abundance. So it suppresses how wide the variation in abundances really is. But we have to do that because if you look carefully here, you can see that the least abundant elements are something outnumbered by something like 1 trillion to 1 by the most abundant elements. So if you didn't put this on a log scale, you'd never be able to even see the stuff that is near the bottom there. So if we look, you can see that the most abundant element in the universe is hydrogen. Where's that in the periodic table? Number 1, right? The very simplest element is far and away the most abundant in the universe. Again, it's a log plot, so this makes it look like helium is almost abundant as hydrogen is. But no, it's actually only about 1/10 as abundant by number. So there's about 10 hydrogen atoms around for every helium atom in the universe. And then after that, the third most common element is oxygen, and then carbon is also a popular element. They're both outnumbered by something like 1,000 to 1 by hydrogen atoms, and everything else is less than that. So the universe is overwhelmingly made of hydrogen and helium. Water is actually a pretty abundant molecule, and we can see that that makes sense because it's made of a combination of the most abundant element and the third most abundant element. Number 2, helium, will it make compounds? Very hard to convince it to do that, right? Because it's a noble gas, it's too good for that sort of thing, and all that. So that's why water is common in the universe. Now, by mass, the sun is about 3/4 hydrogen and about 23% helium, and all the other elements put together by mass, as opposed to by number, make up about 2% of the sun's mass. So astronomers are weird in a lot of ways, and one of them is that we have this funny terminology where to an astronomer, if it ain't hydrogen and it ain't helium, it's a metal. So carbon is a metal, oxygen is a metal to astronomers. We call the fraction of the mass that a star has in terms of metals with our funny ain't hydrogen, ain't helium definition. That's the star's metallicity. And so we say that the sun's metallicity is about 2%. We can look at the spectra of other stars and figure out what their metallicity is too. Some stars have lower metallicity than the sun, but even the most metal-rich stars have metallicities of only about 4%. So that's an important fact, that the universe is mostly hydrogen and helium. Even the most metal-rich stars, only about 4% by mass of everything else. Since I'm talking to women in science, I should mention that one really great thing about teaching astrophysics is I get to talk about many really fundamental, important discoveries about the universe that were made by women. And the fact that hydrogen and helium overwhelmingly dominate the chemical composition of the universe was actually discovered by this woman here, Cecilia Payne-Gaposchkin. So in her PhD thesis in 1925, she was the person who was able to determine that all ordinary stars are made mostly of hydrogen and helium. And it's, to this day, considered to be the greatest PhD thesis ever produced in astronomy. That was back in, I think it was 1925, if I recall correctly. And I mean, I have to say that if you're a graduate student and you figure out the chemical composition of the universe, that's pretty good. You should probably get your degree based on that, right? So not bad. When she did that work, her name was Cecilia Payne, but then she married fellow astronomer Sergei Gaposchkin, and so she got the name Payne-Gaposchkin, which I think is just great. What an awesome name, Payne-Gaposchkin. Anyway, so how did Cecilia Payne do this? How did she figure this out? Well, when we spread out the light of a star with a spectrograph, then we see absorption lines in the spectrum. And those are produced when atoms that are higher up in the star's atmosphere, where it's cooler, absorb photons of specific wavelengths coming up from deeper, hotter layers. And you can see that if we look at this variety of stellar spectra here, that the spectral lines of different elements have different strengths. So in particular, the hydrogen spectral lines, it turns out, are strongest around spectral class what's called A0 here, and then weaker in other spectral classes. And at first, astronomers thought, naturally enough, that that meant that different stars had different amounts of the different elements in it. That'd be the first thing you would guess. But what Cecilia Payne did is take a newly developed equation called the Saha equation and show that really what was going on is the primary determinant of how strong the spectral lines are with variations in the temperatures of the stars. And she was able to show, first people didn't really believe her, but she knew what she was doing and convinced everybody, that in fact all ordinary stars are made mostly of hydrogen and helium with just a little bit of everything else. And so that's why she's famous. So where did the elements come from? Well, it turns out that hydrogen and helium, the two simplest elements and the two most abundant in the universe, those are primordial, left over from the Big Bang, in other words. Hydrogen came almost directly out of the Big Bang, not immediately, it had to cool down a bit. But then when the universe was just a cute little baby, a few minutes old, a lot of the hydrogen fused into helium. And most of the helium in the universe is left over from that initial cosmic nucleosynthesis episode when the universe was a baby, essentially. A little bit of lithium came out of that as well, but also beryllium and boron, lithium is also made today by cosmic rays crashing into other nuclei in the interstellar medium. So are beryllium and boron. They're not made in stars. But everything else is. Everything, all the other natural elements, all the other natural elements are cooked up in stars. So that's a remarkable thing to realize. This is what's responsible for all the atoms in your body except for the hydrogen atoms, and all the elements in Earth except for the hydrogen and helium atoms. They were all cooked up in stars before the sun was born. Amazing to realize. Well, how did we figure this out? Turns out I'm still talking to women in science, which means I should tell you about Margaret Burbidge and the B squared, they got a typo here, B squared FH team. So the mechanisms behind it, let's play read along with the professor, shall we? It's like what I do when I give out syllabi. But anyway, the mechanisms behind the production of the heavier elements, the S&R processes, which I'll tell you about later, were first pointed out in a long theoretical paper published in 1957, Synthesis of the Elements in Stars, Burbidge et al., 1957. This revolutionary and still up-to-date paper is signed B squared FH. Not a strange chemical compound, but the initials of the surnames of the scientists who wrote it: Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle. The British astronomer Margaret Burbidge was born in 1919, and this is from 2007, so I don't know if it's true if she's still active in research, but she's still alive. She's 96 years old now. As Professor Emeritus of Physics at the University of California, San Diego, USA. When she was a teenager, her grandfather gave her popular books on astronomy. I saw my fascination with the stars born at age 4, she writes in her witty autobiography, Burbidge 1994, linked with my other delight, large numbers. Astronomy is good for people that like big numbers, as you can imagine. Her life has been full of scientific discoveries and political fights. It was not always easy to be a female scientist, but she never gave up. If you meet with a blockage, find a way around it, she suggests. The rest of the group is no less notable. Fred Hoyle and Margaret's husband, Geoffrey Burbidge, are most famous for their iconoclastic theories opposing the Big Bang, which have now been essentially discarded, while William Fowler shared the 1983 Nobel Prize in Physics for his theoretical and experimental studies on nucleosynthesis, the building up of atoms by nuclear physics, nuclear fusion. So, here's the big picture. Atoms made by nuclear fusion in earlier generations of stars get returned to the interstellar medium of gas and dust from which later generations of stars and planets are born. So only essentially hydrogen and helium came out of the Big Bang, a little bit of lithium, very little of that. So the early universe didn't have the stuff in it of which you and I and Earth and so forth are made of, other than the hydrogen. That had to be built in stars first. And so we literally owe our existence to thermonuclear fusion inside stars. And I think it's amazing to realize that we are literally, not figuratively, but literally made out of stardust. That's the kind of thing where if that doesn't inspire you, I give up. I cannot possibly reach it. I quit. But I suspect that, especially with this group, that is something that would inspire you, as a matter of fact. Note that even the hydrogen atoms, though, they're not left out, and the helium atoms either, because they've got a pretty cool story, too. They came out of the Big Bang, which is not too bad either. That's about 13.8 billion years ago. So, why do stars fuse lighter nuclei together into bigger nuclei? So first of all, a star represents a battle, if you will, between the inward pull of gravity and the outward push of pressure. And so for the star to be stable, it has to have an equilibrium between those things. Every layer of the star has to be such that the pressure pushing up on it balances the weight of the layers above it. Now, during most of the star's life, the tremendous pressures that are needed in order to keep it from collapsing under its own weight, that's maintained by energy released by thermonuclear fusion reactions inside the star's core, and that keeps the core at temperatures of millions of Celsius. I was debating whether I should say Kelvin You guys probably know Kelvin is just like Celsius, except that it starts at absolute 0. So Celsius and Kelvin differ like, by 273.15 degrees. I figure you probably hear the word Celsius more often, and the difference between 10 million Kelvin and 10 million Celsius, a couple hundred degrees doesn't matter anymore. So I'm just going to keep saying Celsius, even though amongst astrophysicists we always say Kelvin, 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 Kelvin. So anyway, nuclear fusion requires very high temperatures. Probably a good thing, because otherwise, like, the hydrogen in your water molecules would fuse with the other hydrogen, and that wouldn't be very compatible with your continued existence or continuing to listen to this talk or anything like that. It requires very high temperatures. Why? That's because nuclei contain protons. Protons have a electrical charge where equals positive, yes, they're positively charged. So that means that, well, let's see, positive charges with other positive charges. Are they like, yeah, I want to meet up with you, or like, get away from me? Yeah, get away from me, right? Likes repel when it comes to electrical charge. So if you have positively charged nuclei moving towards one another and they're not moving fast enough, they'll just veer off course because of that electrical repulsion. Get them moving faster, and they can get closer together before they veer off course. Get them moving fast enough, though, and they can feel the strong nuclear force, which is what holds nuclei together. It binds protons and neutrons to one another. So if they're moving fast enough, then they can feel the strong nuclear force, and there's a chance that they can bind together and stick, and that's what nuclear fusion represents. Nuclei smacking into one another and forming a bigger nucleus as a result of that. Well, as you probably know, for things to be moving fast, you need high speeds. And high speeds. For things to move fast, they need to be moving fast, Edith said. And furthermore, you need high temperatures, is what I was really trying to say there. So you need high temperatures in order for thermal motions to be very fast. In order to get hydrogen to fuse, you need temperatures of around 10 million Celsius. And you're only going to get that in the core of a star. Only in the core of the sun is the temperature more than around 10 million Celsius, so that the nuclei can be moving fast enough to fuse. And in particular, the sun is turning hydrogen into helium via nuclear fusion. And that is the source of the energy by which the sun shines. All normal stars do this throughout most of their lives, is fuse hydrogen into helium as the source of their energy. So for the sun, the main reaction is called the proton-proton chain. And it starts when two protons collide with one another and stick. One of the protons has to turn into a neutron by spitting out a positron, which is a positively charged antimatter electron, and a very light particle called a neutrino. The positron meets its matter counterpart, the electron, and they annihilate into a pair of gamma rays. And then this gives you deuterium, heavy hydrogen, proton and neutron in the nucleus. And then another proton comes along, smacks into the deuterium nucleus and makes helium-3, 2 protons, 1 neutron. Another helium-3 nucleus made the same way, smacks into that, and you get a helium-4 nucleus, 2 protons, 2 neutrons, and it spits out 2 protons. And so if you look carefully, you can see that 1, 2, 3, 4, 5, 6 protons went in, but 2 got spat out at the end. And so the net reaction is that 4 protons fuse together, 2 of them turn into neutrons, so that you get a helium-4 nucleus. And a helium-4 nucleus has about 0.7% less mass than the 4 protons that made it up. And that quote-unquote missing mass turns into energy by one of the most famous equations in all of physics, due to Albert Einstein. E equals mc squared. E equals mc squared. Energy equals mass times speed of light squared. That's what's powering the sun. It's converting mass into energy via nuclear fusion of hydrogen into helium in its core. All normal stars do that for most of their lives. Meanwhile, there's a secondary reaction in the sun that actually is the primary hydrogen fusion reaction in more massive stars, called the CNO cycle, where CNO stands for carbon, nitrogen, oxygen. And what that does is entails a carbon-12 nucleus fusing with hydrogen, and then there's 2 more hydrogen fusions, which ultimately, after an oxygen 15 decays to a nitrogen 15, another hydrogen comes along, smacks into that, and produces helium 4 plus carbon 12. So the carbon 12 comes back at the end. In chemistry, what you call a reactant that facilitates the reaction but doesn't get used up. It's a catalyst, right? Carbon 12 is a nuclear catalyst here as opposed to a chemical catalyst. It doesn't get used up, but it facilitates the reaction. The overall net reaction is the same. 1, 2, 3, 4 protons go in and a helium-4 nucleus comes out. So this is another way to fuse hydrogen into helium in stars. Now, the sun is huge compared to the Earth. This is a photo that shows, well, Photoshop probably ideal, but anyway, this shows the relative, no, they actually got them in front of the sun and took a picture and then moved them back to their normal orbit. Here is Earth and Jupiter shown in their correct relative sizes compared to the sun. So the sun is more than 100 times Earth's diameter, or as I like to put it to my astronomy 110 and 111 students, and even my astrophysics majors, sun big. Make you want talk like caveman, so big, right, or something like that. Impressive enough, but about 5 billion years from now, the sun is going to have used up all the hydrogen in its core. It's got a lot of hydrogen in its core as fuel, but not an infinite supply. It'll burn through all of it, and then it's going to get really big at that point, as it becomes a red giant. So I'm going to show you the correct relative scale size between sun today, already huge, sun is a red giant. It'll be this much bigger when it's a red giant than it is today. So why is it going to do that? Why is it going to get so big? So the idea there is when the core runs out of hydrogen, then there won't be any more nuclear reactions in it, and so it won't be able to maintain enough pressure to support its own weight. So gravity is going to start winning the battle, and the core will start to slowly shrink as a result of that. And similar to the way where if you, I don't have anything I should, similar to the way if you drop something, then notice that we can say that it turns gravitational potential energy into kinetic energy as it falls, and then it hits the ground, and that ultimately gets dissipated as heat, thermal energy in the end. Even the sound waves eventually turn into heat. When the core shrinks, it converts gravitational potential energy into thermal energy, and so the core actually heats up as it is shrinking, and that heats up the unfused hydrogen surrounding it, and it ignites hydrogen fusion again, not in the core anymore, but in a shell surrounding the core. And as that hydrogen fusion shell creates more helium, it dumps that onto the core, which increases the gravity in the core because it has more mass. So it keeps exacerbating the process of the core shrinking and heating up. And as a result, that heats up that hydrogen fusion shell even more, and it gets to as a result of that, it's fusing hydrogen a lot faster than is happening in the sun today. And the amount of energy being released at a maximum would be something like 2,000 times more than it is now. And all that extra energy raises the pressure in the star's outer layers, and that causes it to swell up and cool and become a red giant star. Meanwhile, all the action is taking place surrounding the core, which is only about the size of the planet Earth. So all the action is in this really tiny center in a star like this. So at its max, as I mentioned, the sun will get about 2,000 times brighter than it is now. So that's something even cockroaches wouldn't be able to deal with. My advice is not to stick around for this, is what it comes down to. So, anyway, as the core continues to shrink and its temperature keeps rising, eventually it'll hit the magic number of about 100 million Celsius, and that's hot enough for helium nuclei to overcome their electrostatic repulsion from one another and start colliding, sticking, fusing together. And because nuclear physicists call helium nuclei alpha particles, this is called the triple alpha reaction because 1, 2, 3 helium nuclei fuse together to make one carbon-12 nucleus. notice 1, 2, 3, 4, 5, 6 protons go in. That's how many protons a carbon nucleus has. And 1, 2, 3, 4, 5, 6 neutrons go in, so it's carbon 12. 12, remember, that's the total number of protons and neutrons. So 6 protons, 6 neutrons. Works out just right. First, what has to happen is 2 heliums fuse into an unstable nucleus, beryllium-8. That'll almost instantly fall apart, but if another helium-4 comes in just in time and smacks into it, then it can fuse into the carbon-12 nucleus. And this is good news for us, because as carbon-based life forms, we're fans of having carbon-12 in the universe, and this is a primary means by which the carbon-12, that's the basis for your biochemistry, was made in stars before the sun was born. Meanwhile, once enough carbon builds up, a helium-4 nucleus can fuse with a carbon nucleus, and that'll add 2 more protons, so the carbon becomes, what's got 8 protons in the nucleus? Oxygen, yeah, oxygen, right? So the oxygen that we're breathing, a lot of it is made by the process of helium fusion in stars as well. Some of the carbon turns into oxygen as a result of that. So you get oxygen-16 out of that, which is the most common oxygen isotope. So, but wait, there's more. After helium fusion in the core settles down to a steady rate, turns out it starts explosively, then hydrogen will still be fusing in a shell surrounding the core, but it turns out that the star will no longer be as bright as it was when it was a red giant. It'll calm down and only be about 50 times as luminous as it is now. But then the core is eventually going to run out of helium, and then we're going to get kind of a repeat performance of what happened when the sun became a red giant for the first time. The helium core shrinks, heats up, ignites a helium burning shell surrounding the core. The carbon-oxygen core itself left over from the helium burning is inert at that point. And at that point, the sun will become a red giant for a second time. And the technical term for that is really kind of odd. The sun will be called an asymptotic giant branch star, which gets really tiresome to say, so astronomers just say AGB star. And you might say, why is it called asymptotic giant branch star? And that's because on a plot, a very standard plot astronomers use of stellar brightness versus surface temperature, then the point that represents the star, when it's an AGB star, asymptotically approaches the giant branch on the diagram. Yeah, whatever. Anyway, funny name, but still quite a spectacular stage. It'll get even bigger than it was as a red giant, even more luminous, max out at something like 5,000 times brighter than it is now. But meanwhile, this is the beginning of the end for the sun, because it turns out that the helium-burning shell will be unstable and subject to flare-ups that last a few decades, separated by quiescent periods that last for millennia. And the flood of energy that comes out of these so-called helium shell flashes, these flare-ups of helium fusion in the shell, will push the outer layers of the sun off into space and produce one of these. This is called the Ring Nebula. It's a Hubble Space Telescope photograph of the so-called planetary nebula in the constellation Lyra. Has nothing to do with planets. It just refers to the appearance that they have to the eye looking at them through a small telescope. And so what we see here are the outer layers of a low-mass star that got pushed off into space by the helium shell flashes. So here we have an example of the return of some nuclei that were made by fusion inside the star, along with lots of leftover hydrogen that never fused and so forth, back into the interstellar medium, ready to be incorporated into future generations of stars and planets. Now, this thing in the middle right here is the leftover, burnt-out carbon-oxygen core, and that's called a white dwarf, and that's what the sun's eventually going to end up as a white dwarf. The sun's white dwarf will have about half the sun's current mass. The other half will have been ejected into space, but it will only be about the size of the planet Earth. And when you pack half the sun's mass into something the size of Earth, you get a density of about 1,000 kilograms per cubic meter. So a sugar cube of white dwarf would have about the mass of a car. And the gravity is so strong that it would weigh about as much as 100,000 cars or so. So you might say, wow, what would it be like to be on the surface of a white dwarf? And the answer is literally nothing, because before you even had time to think, you'd be squashed flat and vaporized and just become part of the white dwarf. So if Scotty ever offers to beam you to the surface of a white dwarf, refuse. Don't do it. It's not a good place to be. So we said that stars are a balance between pressure and gravity. A white dwarf doesn't have any nuclear fusion in it, so you might say, well, why doesn't it then collapse as a result of that? And the answer is that it has a type of pressure in it which is inherently quantum mechanical, called electron degeneracy pressure. So you guys know about the Pauli exclusion principle, which says that you can't put any more than 2 electrons into an orbital in an atom, and they have to be spinning in opposite directions. And this means that you can't put all the electrons into the ground state, kind of where they'd like to be. They're forced to have higher energies. Well, in the white dwarf, the electrons aren't orbiting individual nuclei. They're spread throughout the white dwarf. But the Pauli exclusion principle is still forcing them into much higher energies than they would have according to classical physics. So they're moving, if you will, a lot faster than they would for the temperatures involved compared to what you would get in classical physics. So they're not described by the ideal gas law that relates pressure and density and temperature. Because they're moving so much faster due to the Pauli exclusion principle, they're also exerting a lot more pressure than they would classically. And it turns out that this pressure is enough to permanently support the white dwarf against its own gravity, because even as the white dwarf cools over billions of years, the electrons will still be forced to be in these very high energy, very fast moving states. So a white dwarf, if you will, is a final stalemate in this battle between gravity and pressure, and it's nice and stable. Now you might think that this electron degeneracy pressure is this exotic phenomenon you've never experienced before, but you'd be wrong, because it turns out in a metal, the outer orbitals of the atoms overlap one another so that the electrons are free to move throughout the metal. That's what makes a metal an electrical conductor. The electrons can move, and they have very high energies, much more than you would predict from classical physics based on the temperature, and so they exert a lot more pressure than they would, classically speaking, based on the ideal gas law. There's basically a gas of conduction electrons in the metal, and you can calculate that it exerts a pressure comparable to what you'd predict for the ideal gas law for a temperature of around 100,000 Kelvin. That's why metals are so stiff. It's due to electron degeneracy pressure. So you've experienced it yourself. It's what keeps a white dwarf from collapsing under its own weight. So a low-mass star never goes beyond fusion of helium in its core, but high-mass stars go beyond that. Eventually, a high-mass star's core gets hot enough, 600 million Celsius, to start fusing carbon. And then that keeps going, and you get a whole series of fusion reactions in shells surrounding a core made of iron. And that's as far as it ever goes. Iron, it turns out, cannot serve as a nuclear fuel, so once the star has iron in its core, it is doomed. Doomed, I tell you, because if you fuse anything with iron, it takes energy instead of releasing energy. It's endothermic instead of exothermic, so it can't serve as a fuel. But meanwhile, that iron core, which is again about the size of Earth, it's essentially like an iron white dwarf in the center of the star, it's supported by electron degeneracy pressure, but there's a maximum mass that electron degeneracy pressure can support that's a bit less than 1.5 times the mass of the Sun. There's a shell of silicon and sulfur fusing to iron surrounding the iron core that's dumping iron onto it, so the core's mass keeps increasing and eventually goes over that maximum mass it can have, and within a fraction of a second it collapses. And when it does that, it releases a gigantic amount of gravitational potential energy, and that powers a shock wave, among other things, that blows the star to smithereens. And that produces what we call a core collapse supernova explosion. And the amount of energy that it releases in a short while is comparable, and actually greater than the amount that the Sun will produce over its entire more than 10 billion year lifetime. So these things are amazing events. And here is a Hubble Space Telescope photograph of the remnants of such an explosion. This is the Crab Nebula. because it supposedly looks like a crab through a small telescope to early observers. I've seen it through a telescope. I do not see a crab. It's one of those Rorschach test kind of things. But anyway, whatever. It's the Crab Nebula because it looks just like a crab. These are the outer layers that got blasted off into space when it blew up. We saw the explosion on Earth back in the year 1054, as a matter of fact. Now, once again, you're seeing nuclear process material returning matter into the interstellar medium where it can be incorporated into future stars and planets. Now, you can't see it, but in the middle of the Crab Nebula is the leftover remnant of the iron core after it collapsed. What happens is that the iron core ends up turning into a ball of neutrons that is about 20 kilometers across. And so, to give you a sense of how big that is, here's somebody, Christian Dior, made a Photoshop job of a neutron star compared to Vancouver. And so the neutron star has about the mass of the sun, but white dwarf's impressive enough, compacted as something the size of the Earth. With a neutron star, you've got about the mass of the sun compacted into something that is about the size of a city. And so there we're talking about a density of about 500 billion kilograms fitting into a sugar cube. The gravity is about 100 billion times stronger than at Earth's surface. These things are pretty amazing. Again, it's supported by degeneracy pressure, but this time it's the neutrons themselves that are providing the degeneracy pressure. By the way, you would not want a neutron star to get this close to Vancouver or Earth in general, because this would not be what would happen. Already the Earth, because of the strong gravity, would have been turned into a little thin smear on top of the surface of the neutron star. A nearby neutron star is not compatible with an Earth also being there. It just ain't going to happen. If the mass of the iron core is more than about 2.8 times the mass of the sun when all is said and done, that happens with the most massive stars, then not even neutron degeneracy pressure can stop the collapse. And gravity ultimately wins the battle, and you produce something even more exotic. Anybody who's not an astrophysics major know what that might be? You produce a black hole, as a matter of fact. You get a black hole. You get a stellar black hole. But neutrons themselves are certainly very exotic. Black holes, that would be another talk. Anyway, so we've talked about how you can build things up to iron. But what about stuff past iron? The problem is iron, again, to fuse things with it, it's endothermic, doesn't serve as a fuel, so stars don't go past the point where they fuse stuff into iron as a primary source of nuclear power for the star. But there's lots of reactions that are going on inside the star during all of this. So before we talk about how you get beyond iron, I'll mention that there are what are called helium capture reactions. So, for example, carbon-12 can absorb a helium-4. We've already mentioned that turns it into oxygen-16, 8 protons, 8 neutrons. Another helium-4 comes in, it can turn it into neon-20, 10 protons, 10 neutrons. Another helium comes in, turns it into magnesium-24, 12 protons, 12 neutrons. That means stars have a relatively efficient mechanism for making elements that have an even number of protons in the nucleus. And we actually can see this in the pattern of abundances in the cosmos. Even-numbered elements tend to be more common in terms of how many atoms of them there are than odd-numbered elements do. And so if you look on the periodic table, that translates into, in terms of cosmic abundances, carbon and oxygen and neon and magnesium and silicon and sulfur and argon are all more common than nitrogen and fluorine and sodium and aluminum and phosphorus and chlorine. So the reason for those abundances is that stars have a good way, helium capture reactions, of making the even number of proton nuclei. Now, when it comes to making the elements that are heavier than iron, the primary way stars do that is with neutron capture reactions. The key there is that neutrons, do they have an electric charge? No, they do not. That means there's no electrostatic repulsion that you need to overcome. A neutron can just smack right into a nucleus without having to overcome the electrostatic repulsion, so that's a lot easier to do. And once the neutron does get captured, you get a nucleus that has more neutrons than before. And you may know that if a nucleus has too many neutrons, so to speak, a neutron can decay into a proton. And the way that it does that is to emit an electron that carries off negative charge and leaves the particle with a positive charge left over, and a light particle called an antineutrino. And so this is called beta minus decay because of the negative charge of the electron that comes out, and because nuclear physicists call electrons beta particles. And if you turn a neutron into a proton, have you changed the identity of the element that the nucleus has? You have, right? Because it's the number of protons that determines the chemical species. So a beta decay like this turns it into the element which has one more proton, and if you move one over on the periodic table. Now, nuclear physicists, like my departmental colleague, Dr. Bob Herring-Kay, use what's called the chart of the nuclides to portray what they call the nuclear landscape. So here on the x-axis, we've got number of neutrons. On the y-axis, we've got number of protons. So if I move along a horizontal line, the number of protons stays constant, so I'm keeping the same chemical element, but I'm looking at different isotopes of that element. Remember, isotopes are different numbers of neutrons for the same chemical element. If I move vertically, I'm moving along lines where I'm increasing the number of protons and changing the chemical element. And the black squares represent stable nuclei, ones that don't want to decay. And above and to the left, you have nuclei that have kind of extra protons in them compared to this so-called valley of stability. And that's called the Wild West, so to speak. And then Dr. H.K. calls neutron-rich nuclei, ones that are over here to the right of the valley of stability, he calls that the exotic east. And the idea is that if you've got extra neutrons, they're going to tend to decay into protons and move you towards the valley of stability. If you've got extra protons, they tend to decay into neutrons with what's called beta plus decay. Again, you move to the valley of stability. The further away you are from the valley of stability, the more unstable the nucleus, the faster it decays. And that means that, wow, this is, cooperate with me. That means it turns out that there are two processes, the S process and the R process, that you might vaguely recall I said we'd get to later with the B squared FH paper, that can make these heavy elements in stars. So the S process, the slow process, happens when there's not too many neutrons around. And so that means they don't capture neutrons the nuclei don't capture neutrons very quickly. And so what that means is there's plenty of time, if the nucleus is unstable, to decay by turning a neutron into a proton before another neutron comes along. So they slowly capture neutrons to become new elements. So this is showing how you can build copper, for example, by the S process, starting with iron, which has 26 protons, iron 56, 26 protons, 30 neutrons. If it captures a neutron, it becomes iron 57. Captures another one, iron 58. Captures another one, iron 59. But that's unstable, and it decays to cobalt 59. Capture another neutron, make cobalt 60. That's unstable, decays to nickel 60. Capture neutron, capture neutron, capture neutron, nickel 63. That's unstable, turns into copper 63. Capture neutron, copper, turn into copper 64. So in other words, these neutron captures followed by beta decays can build new elements beyond iron in the periodic table. Now, the primary place where the S process occurs is in low mass stars that are AGB stars, in that last AGB phase of their lives. So you need a neutron source. Turns out there's two of them. During one of those helium shell flashes that I told you about, there's a series of reactions that turns nitrogen-14 into neon-22. And neon-22 fusing with a helium nucleus produces magnesium-25, and it spits out a neutron. And that neutron can then serve as something that can be captured by other nuclei and do S-processing kind of things. Now, meanwhile, after a flash, it turns out that some carbon-12 created during the flash undergoes a reaction where it absorbs a proton and turns into carbon-13, and then that can absorb a helium nucleus, turn into oxygen-16, and spit out a neutron. which serves as a source for S-processing, if you will. The first process turns out to be more important in stars between about 4 and 8 times the mass of the sun. The second process is more important in lower mass stars. And the bottom line then is, here's our friend the Ring Nebula again. So now we can see that it also is returning S-process elements back into the interstellar medium. But it turns out that that's not enough to account for all the elements beyond iron. Turns out that it's about a 50-50 mix between S-process and another process that we call the R process, where the R process stands for rapid. The deal there is that if there's lots of neutrons around, then the nuclei can, even unstable nuclei, can capture a neutron before they beta decay into another type of nucleus. And there are some elements, for example, gold and platinum and silver, jeweler's elements if you will, that need to start with precursor nuclei that have a big excess of neutrons and then do a bunch of beta decays along to the, over to the valley of stability in order to make the final nucleus. So this shows how to make gold, for example. Start with yttrium, 188, capture a bunch of neutrons so fast that none of the intermediate stages has time to decay, and then that can decay to yttrium 196 can decay to lutetium 196, and then that can become, by absorbing a neutron, lutetium 197, hafnium 197 by beta decay, blah, 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 and eventually you produce gold in the end of that. Gold can't be made by the S process because you have to absorb a bunch of neutrons in order to get to this point where then you can decay into gold. So where can we find places where there's enough neutrons around for the R process? We actually still are not sure exactly where R process elements are made, but there's 2 big contenders. One is in supernova explosions, quark-lap supernovae, like I mentioned before, where at the boundary of the newly forming neutron star, there's lots of neutrons around. And so in this very explosive energetic event, you can have a burst of neutrons that can very rapidly build R-cross elements. That's one idea. But it turns out that there's growing evidence that an alternative scenario may be a better explanation for the R-cross elements, and that is pairs of neutron stars orbiting one another, giving off gravitational waves that causes them to lose energy in their orbits, spiral into one another and merge, and the crust of a neutron star turns out to have iron in it that can eventually, oh, stop that. It can, stop that too. That still can. Here we go. Oh, it's always, let's see, where's my finger? Eventually, come on, I want to play my finger. There it is. Okay, wait, here we go. Okay, that can, when the neutron stars merge, that can serve as seeds to capture this huge flux of neutrons that's being released and form our process elements. So these guys are going to spiral together and go boom in a second here and produce what's called a short duration gamma ray burst. We actually see the signatures of these with bursts of gamma rays, which at first, when they were discovered in the 1960s, were thought to be the Soviets testing nuclear weapons. But it was discovered they're coming from all over the sky, and we now know they're extragalactic. They come from distant galaxies for the most part. And back in 2013, some Harvard astronomers observed an afterglow of a gamma ray burst merging neutron stars, and the spectrum of the afterglow is consistent with it being heated by highly radioactive R process elements. So this is suggesting merging neutron stars make R process elements. They calculated how much gold would have been produced by this merger, and the answer was about 10 times the mass of the moon in gold. Which is impressive. That's a lot of gold, right? I'd be rich. We'd all be rich. Beyond our wildest imaginations, except you got to spread it into the interstellar medium. 10 lunar masses isn't that much, astronomically speaking. But the point is then that, you know, I like to note that why is gold rare? Why is gold rare? Why is gold precious? 2 reasons. 1, it's pretty, right? 2 is it's only made in either supernova explosions or neutron star mergers, and those are rare events, cosmically speaking. So that's why gold is a precious metal, for that reason. Now, one more thing. Okay, now I'm on through. Oh, video again. Stop video. All right, one more thing. I want to finish by talking about something close to home, namely the iron in your blood, the iron in weights that you might lift, the iron in Earth's core. Where does that come from? You might think, well, we talked about massive stars build iron in their cores. Maybe that's where the iron in the universe comes from. But the problem is, when those stars blow up, the iron turns into a neutron star, and very little of it gets out. So we need another way to get iron into the cosmos. Well, it turns out that while an isolated white dwarf is stable, a white dwarf in a binary system can blow up good. And this is an example of that. This is a white dwarf supernova that was seen back in 1994. It was the fourth one, ABCD, seen in 1994 in the poetically named galaxy NGC 4526. NGC is the new general catalog. It was new back in 1885 when it was produced. It's still called the NGC catalog. Anyway, the idea there is that if you've got a white dwarf that has an ordinary companion star orbiting it, you can have mass spill onto the white dwarf from the companion star and increase its mass. The white dwarf shrinks due to the increased strength of the gravity, turns gravitational potential energy into thermal energy, heats up, and when it reaches 600 million Celsius, that's enough for carbon fusion to begin. And because degeneracy pressure doesn't respond to changes in temperature, the reaction runs out of control, and you end up undergoing further fusion all the way up to iron, and that gets blasted into interstellar space by the explosion. Another possibility, turns out there's another model where two white dwarfs merge with one another, but either way, the next time you cut yourself or lift weights, I want you to think about the fact that that iron came from white dwarfs exploding billions of years ago in order to form it. The end.